Welcome to Electric Circuit Analysis lecture series. Today we are looking into the current sources in parallel. In the last class we discussed about voltage sources connected in series and parallel combination. Today let us study about the current sources, various current sources or multiple current sources connected in series and parallel combination, and how to consider the equivalence of that. So first let us take the ideal current sources. Ideal current source. Now if there are two ideal current sources connected in parallel, suppose one current of value I1, other current of value I2, then equivalently I can represent this current with a single source taking the algebraic sum of both the current values. So this will be the total current I as a resultant of sum of two currents I1 and I2, I1 plus I2. Now if both the currents are in the same direction, the resultant current will be the sum of two currents. If the current is in opposite direction, if the currents are in opposite direction, say I1 is upward and say I2 is downwards, then as a resultant, the resultant current will be either upward or downward, the current I, and this I will be the difference of I1 and I2, the difference of I1 and I2. So if current I1 is greater than current I2, the direction of resultant source will follow the direction of I1. If magnitude of I2 is greater than I1, then the direction of resultant source will follow the direction of I2. Okay. So this is simple. When I consider two current sources, ideal current sources in parallel, either there will be subtraction or addition of two current values, and accordingly I should be marking the direction. Okay. Now I will go to practical sources. So practical current sources. So practical current sources comes with internal resistance in parallel to the source value. Let the source value of the current may be I1 with the internal resistance of R1 ohms. In parallel, there is one more current source of value I2 having internal resistance R2. So the resultant of this combination can be given as a single current source of the resultant current value. Let it be represented with I, connected a parallel resistance across this source with a resistance value of R, such that the current value I is equals to, since both the direction of current are in the same direction, I can take I equals to I1 plus I2. Okay. If suppose these two are in opposite direction, then I take I1 difference I2, and the value of R is given by R is equals to, now R1 and R2 fall in parallel combination, therefore I should be taking the resultant of parallel combination. So R is equals to R1 R2 over R1 plus R2. So this is how I can represent a current source, a multiple current source in a single equivalence. Okay. Suppose if the direction of I2 is opposite, then I will take here I1 difference I2 and I assign the resultant direction as that of the larger value current source. Okay. So this is how we go ahead with getting the equivalent current sources when they are connected in parallel. Now what if the independent current sources come in series, current sources in series? So when two current sources come in series, suppose between terminal A and terminal B, let this be current of value I1, let this be the current of value I2. This connection will be valid as we know that in any branch there can't be two currents existing simultaneously. Therefore, there is no meaning if I say current I1 and I2 are the source values of two current sources of different value. Therefore, the connection is valid. Okay, the connection is valid with two current sources falling in series in the same branch if and only if I1 is equals to I2. In case if I1 is not equal to I2, the connection is invalid. The connection is invalid if I1 is not equals to I2. This is an ideal case. These are the ideal sources. Okay, I can take this as ideal case. Now, what happens when two current sources that are practical in nature are in series? So, let us consider practical sources. Okay, practical sources falling in series. Let us consider a current source of value I1 and a current source of value I2 are connected in between the terminals A and B in the same branch. This I1, let this be I2. I1 is having its internal resistance R1 connected in parallel to it. R2 is having an internal resistance of R2 connected in parallel to it. Now, these are the practical current sources falling in series. So, when it was the ideal case, we observed there can't be the connection of two ideal current sources in series if the two values are different. Now, but in practical case, I can analyze this circuit and still find the equivalence of these two current sources falling in series. Now, we know in the source transformation I can convert or I can transform voltage source into a current source and current source into a voltage source. So, therefore, I can now convert or transform both current sources into voltage sources, then I get two practical voltage sources falling in series. And we already have seen in the previous lecture that two voltage sources falling in series can very easily be analyzed, okay, or obtained with the equivalence of the values. Okay. So, what we will follow here is transform both current sources into voltage source. Both current sources into voltage sources. So, from terminal A, I will take a voltage source. I will take one more voltage source connected to terminal B. Okay. So, let this be E1. This is the internal resistance R1. Let this be E2 and the internal resistance R2. Now, the direction of E1 and E2 observe should be along the direction of the current sources. The direction of E1 and E2 should be along the direction of current sources. Okay. So, towards where the arrow mark is heading to, that side I should be marking the higher polarity or the positive polarity of the voltage source. Okay. And this E1 and E2 are given by E1 is equals to this I1 into R1 and E2 is equals to I2 into R2. This we have seen in the source transformation. Okay. Now, when two voltage sources are connected in series, I can very easily get the equivalent of those two sources. I can get the equivalent between A and B represented by a single voltage source and a single resistance. Okay. So the direction of both the voltage sources are in the same direction. So the resultant will be the direction of both E1 and E2. Let me call this resultant voltage as E, it is E, and the resultant resistance as R. So here E is equals to, the direction of both E1 E2 are same, therefore E is equals to E1 plus E2. If the directions are opposite, then E1 difference E2, and R is equals to, it is R1 plus R2. So this will give the resultant equivalent circuit. Now if I want the equivalent current source, the main motto of doing this is, there are two current sources connected in series. I want the equivalent current source connected between A and B. So now as I got the equivalent voltage source between A and B, I can now convert this into a current source. So we can transform this voltage source into a current source. I can put a note here, transform the voltage source into current source. Now between A and B, I can take a current source across which I can show a internal resistance which is of R ohms. The same R ohms comes here, and the direction of E is from A to B, therefore the direction of current source will be from A to B with the current value of I, and this current I is given by E over R. Okay. So even when I have two current sources in series which are practical in nature, still I can get the equivalent current source between the two terminals by transforming the original current source into voltage source, taking the resultant of voltage source and getting the equivalent voltage source between the terminals, and then transforming the voltage source back to current source. So this is the method which we follow to get the equivalent current source when multiple current sources come in series, that too are practical in nature. So next point of discussion what we would like to move to is the source shifting. So far what we have seen is the source transformation. Okay. So here we transform sources from voltage source to current and current to voltage sources. Now I would like to discuss the source shifting technique. Now what does this source shifting mean and why we should follow this or why we need this? Now suppose I want to reduce the entire network into a simple single equivalent circuit consisting of a single source, and I cannot directly transform the voltage source to current source or current source to voltage source where my source transformation stops. So for example, I would like to give a simple circuit. Okay. Suppose I have a resistor. Let us consider this circuit having some voltage E. Transformation which we would be studying in forthcoming classes. Then I take equivalent resistance which comes in series with this E, then I can represent this with the equivalent current source or equivalent voltage source. But in first place I cannot take the source transformation directly by looking into the circuit orientation. But still if I want to go for source transformation, then I need to shift this voltage source in the other part of the circuit equivalently and then take the transformation. Okay. So source shifting we use whenever we get struck with the source transformation. Wherever the source transformation stops, I would like to introduce source shifting there, then again the source transformation can be continued. Okay. So what are the principles of source transformation or technique of source transformation we should see. So whenever I transform the source, I should always keep it in mind that the transformation should be equivalent transformation. Okay, so the branch currents and the node voltages should not get changed. Okay, the branch currents and the node voltages should not get changed whenever I do the source shifting. Shifting in the sense I am taking this voltage source from this branch and placing it in some other branches. Okay, so let me continue with a typical circuit where there is a better possibility of source shifting rather than this. Okay, so for a moment I will erase this. Let me consider a circuit. So let this be a voltage source of E volts. This is an example circuit just to understand the source shifting operation. So let me name the resistors. Let this be R1, let this be R2, let this be R3, and let this be R4, and let this be R5. I will name the nodes. Let this be node N1, node N3, node N2, and node N4. Now I will, for my convenience, I will also name the terminals for these all resistors. Let this terminal of resistor be A, let this be B, let this be C, let this be D, E, F, let this be F, let this be G, and let this be H. Okay. Now I would like to shift this voltage source from its main branch to the other branches. Where all I can shift the voltage source? One thing we should remember when shifting the voltage source is that I will write a note here. Note. Voltage source can be shifted. Voltage source can be shifted to all the branches. Can be shifted to all the branches connected to the same node. Connected to the same node where the voltage source is connected. Now this voltage source of E volts is connected to node N1 and node N2, which is directly connected to node N1 and to node N2. So I can shift this voltage source either beyond this node N1, that is in branch AB and in branch CD simultaneously, or it can be shifted beyond this node N2 either in branch EF or GH simultaneously. But simultaneously I cannot shift this voltage source in branch AB and CD, EF and GH at a time. So always whenever I want to shift the voltage source, I can push this voltage source beyond one node, either ahead of it or previous to it. So either I can shift this voltage source or push this voltage source beyond node N1 in all the branches connected to node N1, or beyond node N2 in all the branches connected to the node N2, but not simultaneously beyond N1 and N2. Now when I shift this voltage source beyond the nodes, what happens to the original branch? Now whenever I shift any source from its original branch to the connected branches, then the value of that voltage in the original branch should be made 0. Okay. So this statement continues. Voltage source can be shifted to all the branches connected to the same node, and by making voltage value 0 in original branch. Now how can I make a voltage value 0? We know that voltage is 0 across short circuit. Okay, that is by replacing voltage source by short circuit. That is by replacing voltage source by short circuit. Now when I push this voltage source E beyond either node N1 or node N2, then the original branch is to be replaced by short circuit. Now I will do that exercise by pushing this voltage source. So let me draw the same circuit again. So this is a node N1. So in this node N1, I am connecting the voltage source in both the branches. This is R1, this is R2. This is R3 and this is R4. Now the original branch, in the original branch, the voltage source is replaced by the short circuit. We have a resistance R5. This is R3 and this is R4. Okay, when I compare the two circuits, the original branch is now replaced by a short circuit. So you can see a short circuit here, and this voltage source E is pushed beyond the node in all the branches connected. Now there are two branches connected to this node N1. There are two branches connected to this node N1. Okay, therefore I have pushed the voltage sources connected to both the branches connected to this node N1. Fine. Now what happens with the polarities? How should I replace or assign the polarities? Simple. Now the direction of this E is clockwise. You shift this voltage source in the same direction. Observe here, with this polarity of E1, node N1 is at positive terminal or a higher potential point, node N2 is at lower potential point. It means terminal A of R1 is at positive potential, terminal C of R2 is at positive potential. So when I shift the voltage source beyond the node, the respective terminals should have the same polarities, that this terminal A of R1 should be positive and this terminal C of R2 should be positive. It means the polarity of E should be in such a way that the original polarity of the terminals should not be lost. Hence, the polarity assigned should be in such a way that A is positive, C is also positive, and this is the voltage E. When this was the polarity, observe here, N2 was at negative potential. Now when I connected this or shifted this voltage source, this N1 is at negative potential, N1 is directly connected to N2. This is N2. So N1 and N2 are connected to the same node. It means N2 is still at a negative potential. So even after shifting the voltage source beyond the node, the potentials of the nodes have not changed. Okay, the potentials of the passive element terminals have not changed. If this care is taken, okay, then it is said to be having the successful shifting of voltage source and correct way of shifting of voltage source. And one thing also you can observe here, the direction of E. The direction of E is clockwise, so the direction of E in both the branches is clockwise. So even if you blindly shift this voltage source along its direction, it will do the work. But you should make sure that this voltage source should be connected or shifted in all the branches connected to that node. Now when I shift this voltage source beyond node N2, okay, if I shift the voltage source beyond this node N2, my R1 and R2 will remain as it is. Again I will be replacing the original branch by short circuit. So let this be R1, R2, R3 and R4. Now this is the voltage source shifted beyond node N2. This is N1. Now in the original circuit, E and G terminals of R3 and R4 respectively are connected to N2, which is at negative potential. So it means terminal E is at negative potential, terminal G is at negative potential. I have to follow the same potentials. So here I should mark the potentials of shifted source in such a way that the original potentials of both the terminals of both the resistors are kept as it is. So this is E, this is E. Now N2 is at positive potential, directly connected with N1. Now N1 is at positive potential. So as R1, terminal A of R1 and terminal C of R2 are still at positive potential. So when I have shifted voltage source, the node voltages should not change. The node voltage should not change means what? The potentials of the terminals of all the elements connected to any particular node should be unaltered. That care has to be taken and we have to shift the voltage source. Okay. So when I observe the original circuit, see the direction. So the direction of E is clockwise in the original branch, still the direction of E is clockwise in the shifted branch. So this care has to be taken whenever we are shifting the voltage sources. Okay. Next we shall see shifting of current source. Let me consider a circuit, any random circuit, where I can effectively illustrate the shifting of sources. Now suppose I have a current source of I amperes. I have a resistor R1, resistor R2, R3, R4 and R5. So once I shift the sources, say for example in the voltage source here, now I have a R3 resistor in series with E, then I can go ahead with the source transformation and follow. Okay, that we will see when we take a particular example to solve. So here my I1, I can't transform this current source I into voltage source directly because there are no direct parallel resistance connected to this independent current source I. To do the or to facilitate the source transformation, okay, now I will be doing source shifting, where all I can shift the current source. Voltage source we have seen, I can shift voltage source in all the branches connected to that particular node. So here current source can be shifted across all the branches connected in parallel to the current source. Can take here a current source. A current source can be shifted, not can be, is shifted. A current source is shifted across all the branches, that are in parallel to the original branch of current source. Original branch of current source. Then what happens to original branch? And current in original branch is made zero. Current in original branch is made zero by replacing current source by open circuit. By replacing current source in original branch by open circuit. So now here I have this current source connected across the branches of R1 and R2. Now the branch of R1 and R2 are coming exactly in parallel to the current source I. Therefore, I can shift this current source I across R1 and across R2 simultaneously. Okay, by following the direction of I. Okay, so let me name the nodes here again. Let it be A, let it be B and C. Other nodes are not necessary, so I will leave it as it is. Okay, now follow the step here. This is my original circuit. Now I would like to shift this current source I across A and B or across R1 and R2. Okay, I will be following this. A current source is shifted across all the branches that are in parallel to the original branch of current source. So this is the original branch of current source. Okay, the branch AC is the original branch of current source. It has to be shifted across all the branches that are in parallel across current source. So branch AB is in parallel, branch BC is in parallel directly. So therefore now I will shift this current source across R1 and R2 in such a way